Welcome to today's webinar, Building a Data Lake on AWS. Our presenter today is Ian Myers. Ian has been working with data management systems from the beginning of his career. Working as a developer, database administrator, and architect, he has been involved in projects spanning local government, telecoms, internet gaming, investment banking, energy, utilities, and also automotive. At AWS, he works with customers to build high-quality, accurate, and durable data management platforms, which push the boundaries of scale, agility, and performance. He is based in the United Kingdom and works alongside other specialist SAs for security, networking, HPC, gaming, storage, SAP, and Microsoft, to name but a few. Also with us today, we have Motaz Anani, Solutions Architect, and he will engage with you and answer your questions throughout the presentation while our presenter presents. Ian, welcome. I now pass the floor over to you.
Thanks very much. It's great to be with you today, and we're going to do a replay of a session that was originally given at reInvent, our annual global conference for all things AWS. It was called BDT 317, and the recording of that is available on AWS's YouTube channel. So today we're going to talk about building a data lake on AWS and what are the patterns and concerns that you need to include in these types of applications and how to maintain best practices, cost effectiveness, and well-architected status. It's important to think about where we're going and also where we've been and what is the legacy that we're building on top of for the data lake. Historically, the enterprise data warehouse was the center of the database and data management engineers universe, and it provided some significant benefits to the business and to engineering. It gave us a really powerful ability to create a schema for data that was available to all of our end users, that was self-documenting, that had usually very clean aspects to the quality of the data, to the representation of data and the consistency of that data. In enforced data types, it gave us a very consistent and common security model that was very easy to develop against and easy to audit. And it also gave us really simple tools for access. SQL is very easy to find skills for in the marketplace, very easy to take up as an analyst coming from perhaps a background doing analysis with spreadsheets. And it had a fantastic ecosystem that allowed us to see really good business intelligence tools and also gave us a transactional aspect to data whereby we could load data that was ACID in nature, atomic, consistent, isolated, and durable in nature. And these were fantastic properties that have really allowed us to build very powerful decision support systems for our businesses. But one thing that the enterprise data warehouse does do is couples the storage of data with the ability to execute processes against that data. We have compute and storage merged into a single environment that gives us these great attributes, but doesn't really give us a lot of ability to change and be flexible about the kind of tools that we use to access our data. And over time, we found that there are additional requirements for working with streaming data, doing machine learning, to be able to do natural language processing, to be able to be very fast and flexible about the types of data that we ingest, and to work with things like social data. And the enterprise data warehouse gave us some ability to work with this type of data, but certainly we have found that there has been the rise of big data in the marketplace. Big data and generally the Hadoop and Spark ecosystems have meant that we can have very good flexibility and agility in working with new types of data, and in some cases has superseded the requirements of our enterprise data warehouse. So one thing that the big data platforms give to us is the ability to separate compute and storage, and then to capitalize on the ability to deploy lots of different types of computations on top of that stored environment. We can choose whether we want to access our data with SQL or perhaps if we'd rather have a more programming-like environment to work with the data. We can do extracts so that we can manipulate them in a spreadsheet, and we can also push computations right in line with the data, similar to the way that we might have used an enterprise data warehouse. So by separating compute and storage, we get some significant benefits which we need to contrast to the model of an enterprise data warehouse. We're able, firstly, to be able to store all of our data, but without necessarily having to provision extra cores that are used most of the time for storage and only once in a while for processing. We can also become much more granular about how we do things like cost attribution and be able to assess storage within different storage environments, and also to vary the type of storage that we provide for a given piece of data. We also get a massive benefit in that because we can deploy different compute for the storage that we've got available, we can choose different tools that are more appropriate for a specific job to do. We don't have to only use SQL as a data access mechanism. We can also take advantage of storage systems that allow us to increase the durability of our data without having to increase the operations. And by durability, we mean the likelihood that our data is going to be there tomorrow without us having to manage servers and disks and network. We also are able to store our data still with a common representation, a common model, but without enforcing how people go and get at that data. We can have a schema, but also allow people to only pull out the portions they require at a point in time, or to project it into lots of different models. So if we compare a traditional data lake, a traditional data warehouse to a data lake model or big data model, we really need to view them as complementary technologies. Big data and data lake architectures give us the ability to model our data when we go to read it. We don't have to ingest and cleanse our data before we write it down. It has great ability to store semi-structured data, but for the data that is fully structured, we need to take learnings from the enterprise data warehouse world about how to maintain a consistent schema. Big data and data lake architectures are extremely fast to allow ingestion of new types of content. We don't have to do that modeling up front in order to be able to write data down. And we can store data at very, very low level of granularity, as opposed to the data warehouse where often we have storage constraints where it's very expensive to store data. And we get a lot of flexibility. And the two really are complementary. But we get into a problem of who becomes the trusted source for data? Is it the data warehouse that's the final source of truth? And then how do we extend that with big data tooling? If a customer has built something internally using a big data stack, how do we ensure that that same data is available within a traditional data warehouse environment? And so we really need to be able to merge these two concepts together and unify them. And a data lake gives us the ability to do that extremely well. It allows us to ingest any type of data and do data cleansing and prepare data into a data catalog, which can then be exported into the data warehouse for things like structured analysis, for using traditional business intelligence tools, doing ultra-fast aggregation, and having very well-structured business rules. But out of that, we can also take pre-aggregated data to be able to do things like trend analysis or machine learning. And this becomes a virtuous cycle where the learnings that come out of unstructured data sources is pushed into the data warehouse for structured data management processes, and then those business rules come back into a data lake and big data environment. Today we're going to talk about the components that we see as being essential for making a data lake strategy effective. The foundation of that is data storage and the ability to work with streaming data. Our data storage layer needs to be extremely highly durable. It needs to provide us the ability to store raw data without having to do a lot of planning in order to write that data down, and be able to support any type of data. And crucially, because we want to be able to support any type of data, it needs to be low cost and cost effective. Streaming data complements raw storage in the ability to build real-time analytic systems and also to merge the worlds of things like Internet of Things or Twitter feeds with the data storage that underpins our analytics processes. Catalog and search sit above the storage and streaming layer and give us the ability to understand metadata for our data storage tier. For instance, how much data do we have? How much of that data needs to be protected? And the search tier gives us the ability to discover patterns in our data and to have much more robust access for things like data discovery. We also put security and entitlements at the heart of our data lake. And an entitlement system gives us, of course, security, but it also gives us more abstract concepts like authorization, chargeback, being able to apply quotas, to be able to do data masking, or regional data movement. So entitlements is certainly much more than a base of just encryption. Although some of your data and your data classification requirements may be to encrypt it, you also need to control and charge for access to that data within the data lake. And then at the top level, there's the need for an API and a user interface that respect the entitlements capability and which take advantage of catalog and search services that we deploy on top of our data lake. So let's dive into these in some depth. So the storage tier on AWS is focused on giving us very high durable storage at a very low cost. And S3 is absolutely at the heart of AWS's data lake strategy. The simple storage service is web-scale object storage that allows you to store files with virtually unlimited capacity over time, and which is designed for extremely high durability. We talk about 11 nines of durability as the design for S3. And what that means is out of 10,000 objects, you could theoretically lose one of those in 10 million years. And that durability is provided by us managing the storage service on top of multiple availability zones, where each availability zone in a region is one or more data centers on AWS. We actively replicate that data and check it to make sure that it isn't corrupted, and we do checksumming and expose the data fidelity and integrity out to you as a consumer of S3. There are no single points of failure, and S3 provides us a really nice way of applying our security controls, for instance by taking advantage of automatic server-side encryption. As I said, S3 is virtually unlimited storage for the internet. You can have objects from 1 byte in size up to 5 terabytes for an individual file. And within S3, you provision buckets, which are used to store your data, and a bucket can have an unlimited amount of objects within it. With S3, you only pay for what you use by the gigabyte per month, and you're able to take advantage of capacity on demand with no upfront contract. So if today you would like to ingest 100 terabytes of data into S3, you may absolutely do that. Ingest the data, set up the security that you require, and push the data in without ever having to get involved with capacity planning or worrying about whether or not we have enough capacity within the S3 service. Tomorrow, you may ingest nothing, and the next day you may ingest even more. And that flexibility is extremely essential to business users who may have an idea that can draw significant revenue in the marketplace and require the ability to store their data in order to prove that idea. With S3, we can take advantage of multiple tiers of storage as well. S3 supports a feature called Storage Lifecycle Integration. With Storage Lifecycle Integration, you can set a policy that will dictate how data is stored and moved across different storage tiers. At the top level is S3 Standard, designed for 11 nines of durability and always-on operation. The next level down is also designed for 11 nines of durability and gives you immediate access to data, but offers a 60% cost savings over S3 Standard. S3 Infrequent Access lowers your storage costs, but has a charge associated with retrieving data, and is ideal for data that you need to write down once, and then potentially only retrieve very, very infrequently. At the lowest cost option, we have Amazon Glacier Storage. Glacier is designed for cold storage of data that does not need to be retrieved very frequently, and again is designed for 11 nines of durability. Cost reductions are significant over even S3IA and vary by region, but give us immediate access to storing data at any scale. What we get as a trade-off for that reduced storage cost is a 3 to 5 hour retrieval time should we wish to pull the data back, and again, storage charges apply for retrieving that data. And the storage lifecycle integration feature will allow us to move data between those tiers automatically based upon access times, for example. And S3 takes responsibility for that and moves the data based upon the policy you set so that you can tune the cost profile of the data that you're storing. So for example, if you have a data set that you don't know what its value will be, but you expect that you may want to retrieve it at some point in the future, you may ingest that directly onto S3 infrequent access storage to lower your cost and then allow you to move it to S3 standard if it's a data set you're routinely going to be accessing. What is it then that you're going to store in S3? Well, all different types of data may have benefits of being stored in different ways. And what that means is that you can't necessarily pick a single data format that you'll use for all of your data. You need to consider whether your data is unstructured in nature, for instance, log files or forum postings filled with lots of natural text, or for instance, semi-structured data, like JSON data, where you have a schema, but that schema can change over time. Other data storage formats might be really suitable for very structured data like CSV, where we've modeled that data up front and we can very efficiently store it. What we would say as a general best practice is that you store a copy of your raw input data because it allows you to regenerate all the different types of data that you may require at some point in the future. By writing down a raw copy, you're always able to go back to the source and replay an analysis or a model that you might want to do some additional analytics against. And in fact, you probably want to choose a data format that will be sympathetic to the type of data you're storing rather than trying to specifically force your data into a certain type of format. What we would suggest, though, is that you also apply things like a common compression. Choosing a compression mechanism will allow you to work with tools that support that type of compression and which are optimized for access. So, for example, if you were going to be doing lots of big data processing, you might want to use a compression mechanism that supported streaming decompression as opposed to file-based decompression because it can make the decompression process more efficient and can allow your processes to access data very, very quickly. So what are you actually going to do? Well, probably unstructured data we're going to store in its native format. Whatever it is you receive from the data source, you should just store that exactly as you've received it. But often it can be very useful to use a streaming codec like LZO, Snappy, or bzip2 because we'll then be able to get at that unstructured data with tools like Hadoop or Spark that will decompress and work with that data in its raw format and take advantage of the streaming codec. Semi-structured data like JSON or XML files really need to be considered not just for what their structure is at a given point in time, but how that structure is going to change over time. This is what we call an evolvable schema. And your ability to deal with that change over time is something you should evaluate before you choose a data storage format. So a great example is to use Avro as a way of storing data, which gives you the ability to evolve the data schema over time, but work with all of your data using a single definition, which is the final definition of that data. And of course, we have to realize that, of course, lots and lots of data is character-separated values. And we will be storing lots of that type of data in our data lake. We're seeing that tools like Orc and Parquet give us great benefits for applying columnar storage formats to this very structured data. Orc and Parquet effectively store data not as rows, but as columns, and therefore give us very, very high compression rates and very, very fast read rates when we go to access that data. But really is only suitable for data where we know the structure up front and we think it's fairly stable. Also, we need to consider where on S3 we store this data. S3 uses what we call a flat key space, which means that instead of being organized like a file system where you have directories or folders filled with data, in S3 every object sits at its own path, what we call a prefix. And so when you want to change a bunch of objects' prefix, you have to go through each of the objects and update that data. You can't just go and rename a folder like you could in a file system. And so planning the structure of your prefixes up front can offer significant benefits. We tend to see customers separating their data storage within the prefix by using naming conventions, where, for instance, they encode the business unit that owns the data, the application that published that data, even the type of data that's being stored, and absolutely including time as a natural aspect for how data is organized within S3. What this means is that we probably want to organize our data by year, month, day, and potentially even down to hour, so that we can take advantage of that native sorting and the natural data partitioning that we get from S3. Overall, it is very good for paths or prefixes within S3 to be self-documenting and intuitive. A simple litmus test is if you look at a given file, you should be able to tell roughly what that file is and what it contains on the basis of its path alone. But keep in mind that if you want to change the prefix structure at some point in time in the future, it can be very costly and very complex to go through and ensure that you're reorganizing the data that you want to and not touching data that you don't want to. So the benefit up front of doing this planning and deciding on some sort of a convention pays dividends in the long term. And this sounds a lot like something called resource-oriented architecture, which is a system designed and thought about for organizing data on the web, where we organize data based upon its representation, and then we apply operations to that. If we take that model and apply it to prefixes, we can see that we might have a prefix which is the system, the application, the date format, the resources included within that file, and then even things like what security has been applied to that data, what its data classification is, and so on. This makes our data lake storage, the S3 heart of what we're basing our architecture on, to not just be a storage environment, but also to act as an integration layer, where we can look at the contents of that environment and be able to apply policies and create workflows around data. Streaming really complements the data storage aspect because we have the requirement, of course, to do things like low latency and real-time analytics, but also because many data streams simply need to be stored long-term, and with that principle of storing data at rest in raw format. Streams really matter because historically most BI systems would have a latency between an event occurring and then being able to do the analysis of, say, an hour. And in streaming analytics, we really need that latency to be significantly reduced to something like 1 second, 2 seconds. Your business case may dictate significantly shorter latency. And by orienting our architectures around streams, we get the ability to create the storage on S3 through a simple archival process, but also then to deploy real-time analysis to any type of data. This can be a very simple architecture to build, but you do need to consider the complexity associated with managing streaming and raw storage. And in some cases, you can take advantage of AWS services in order to make this process very, very simple to manage. The streaming service that complements S3 is Amazon Kinesis. It's designed for real-time big data processing. You create a stream on Kinesis, and you can scale that up and down over time to meet your performance requirements. On the front end, Kinesis can ingest data from millions of producers, and on the back end, we create Kinesis-enabled applications or use streaming analytics tools like Spark to analyze the data that's coming off the streams. Kinesis is integrated with tools like S3, Amazon Redshift, which we'll talk about in a little while, and DynamoDB, which is a fully managed NoSQL database. With Kinesis, we're able to take all of our data sources and push them into the Kinesis service through a single endpoint, which is made durable across multiple availability zones in a region, similar to S3. Data within Kinesis streams are organized in shards. A shard is a basic unit of capacity, and it gives us the ability to write down 1 megabyte a second or 1,000 events per second, whichever comes first. But a stream can have as many shards as required, and there's no practical limit to how many shards can be included in a stream. So we can add and remove shards to give us just the right amount of capacity to either deal with the amount of data that's coming in or to facilitate the back-end applications that might be doing simple archival and ingestion of that data to S3, doing something like sliding or tumbling window analysis using a tool like Spark Streaming or Storm. If we would use Amazon Kinesis Firehose to load data directly into Redshift, which is our managed parallel data warehouse, or giving us the ability to build event processing systems directly within Amazon Kinesis-enabled clients. The relationship between our storage tier and the streaming tier is such that we want to store the stream of the archive forever, but also be able to replay historical data onto a stream. And again, this is where encoding date and time into the prefix on S3 can be extremely useful. Our analytics applications will be reading and writing from those streams for real-time purposes, but for batch purposes, we'll also be reading and writing file data off of S3. And we're able to create a virtuous cycle where analytics applications are consuming data in real time and potentially then generating archival data, which will be loaded into other systems for subsequent analysis. Let's move on then to the catalog and search tier, which gives us the ability to discover data within our storage and streaming tier, and also to get summary statistics and manage metadata. So a data catalog really gives us that aggregated information about what it is that we're storing within the data lake. It gives us ownership information, it gives us data lineage, and it gives us an abstraction so that we're not only using conventions within S3, for example, as a way of understanding what data we have. A great example that I like to use is, show me all my customer data. Well, my customer data could be spread out across lots of different locations on S3, and a data catalog gives us a simple ability to bring all of those prefixes together and do something very useful with them. The catalog will enable data discovery. Someone can connect to the catalog and say, well, I thought I was interested in customer data, but it turns out that I'm also interested in customer subscription data. And they get information on how that data is organized, and it provides an API, which we can then integrate for the purposes of entitlements, meaning security, authorization, and quotas. So the first component of our data catalog is a metadata index. The metadata index needs to store information about what it is we have on S3. This might be the total size of the data that we've stored, the count of objects. It might break down information by data classification. It might show how often that data has been refreshed, and also give us information about versioning, one of the native features of S3. One of the features that we can use of S3 is a feature called S3 event notifications. A simple pattern for building a metadata index is that S3 events are fired when we store new data in S3, and we use AWS Lambda, which is a serverless compute infrastructure, to process those events and manage a metadata index in DynamoDB, which is a fully managed NoSQL database. We like this pattern so much that we've written an article about it. And in fact, there's sample code that you can take advantage of to maintain this pattern. The URL that you see on the slide currently is going to be, of course, made available as part of the slide deck, but certainly feel free to take a note of that now. So DynamoDB becomes our metadata index storage. DynamoDB is a fully managed NoSQL database service that allows us to scale up and down with extremely predictable performance and gives us ultra-high durable storage. With DynamoDB, we store data again on multiple availability zones for durability, and we're able to scale up and down by adding read and write capacity as needed. DynamoDB is what looks a bit like a column family database, but also supports a document interface so that we can interact with DynamoDB in a similar ways that we would with MongoDB or with a model similar to Cassandra or HBase. Again, fully managed. You, as a user of DynamoDB, simply create a table and tell us what indexes you require. We do all the sharding, partitioning, and heavy lifting on the back end to ensure that you get the provision throughput that you've requested for that database table. We mentioned AWS Lambda, and this is one of our very exciting services that is facilitating very interesting patterns for integrating data within a big data and data lake stack. AWS Lambda is a fully managed event processor that allows you to code in Node.js, Java, or Python, and only pay for the execution of logic that is being fired against events. You don't have to worry about managing servers. Instead, you focus just on your business logic. When you create an AWS Lambda function, you specify the amount of memory that you want to give it and how long you're willing to let it run. And a Lambda function can run for up to 5 minutes to process events from S3, SNS, from DynamoDB tables, which are changing, or from Amazon Kinesis. And as with many of our services, we have integrated logging capability through the CloudWatch monitoring service. The other component for our data catalog is search capability. Search gives us the ability to pre-process our data so that we can do things that are very typically implemented for search indexes, for instance, stemming or stop word removal, downcasing, everything that makes it easy for us to search through our data and not have to worry about the formal structure that we ingested. It will do ranking and relevance calculations, it will do indexing and matching, and gives us a very, very simple environment to find new data regardless of where it's been stored. Two services that are worth considering when you build a data lake are Amazon Cloud Search and Amazon's Elasticsearch service. These are two search capabilities that give you either Elasticsearch, of course, or Managed Solr, and without you having to worry about the operations of those services. We give you a lot of the high availability features that you would require, like automatic recovery of a search domain, multi-AZ performance, and we get extremely high throughput by taking advantage of in-memory caching. And you don't have to worry about provisioning capacity. Instead, Cloud Search and Elasticsearch will scale up and down transparently to deal with the volume of searches that are going through. Services like Cloud Search via Managed Solr or Elasticsearch then give us the ability to do things like faceted search and categorization. It will do relevance calculations that say this is more relevant to that. It will allow us to do things like geospatial search and do relevance ranking and suggestions. Very, very important features for data discovery. Building a search index can also be achieved using AWS Lambda by receiving, again, those same S3 updates for data occurring, being stored in S3, and then updating not just the metadata index, but the Cloud Search index. One of the ways that we can trigger this is that when a file has been added to the metadata index, our DynamoDB table is updated, and we use a feature called DynamoDB update streams to process the fact that that file has been added to the metadata index. We then extract the relevant search fields out of the object and update our Cloud Search or Elasticsearch domain with the relevant searchable data. So an overall architecture looks like what you see on the screen now, where AWS Lambda is receiving events from S3 and from DynamoDB based upon new objects being created or the metadata being updated. And then we maintain that search index over time to allow us to find the data on S3 using a variety of more robust options than just using the prefix that we've provided. Entitlements are integral to working with a data lake storage system. This is security, but also the softer aspects that you may or may not require with your data lake. For instance, chargeback, quotas, and regional restrictions. It's important to note that in many cases, customers do not want to enable raw open access to S3 in their data lake architecture. They require the ability to apply significantly more security controls than just whether or not a user can find a specific object. And so you may find that you want to allow raw native access to S3 for your data lake, or you may find that you require a more robust security model. That security model should be built on the Identity and Access Management System, which is inherent to AWS and provided free of charge and always is used by AWS services for security. It allows you to manage users, groups, and roles of your system so that you can secure assets on S3 or the ability to call AWS APIs like DynamoDB or Kinesis. Identity and Access Management System is based upon a powerful policy language. The policy language in IAM gives us the ability to take advantage of dynamic contextual information about a request being made, including things like, was the request for using a secure transport? Was it based upon a specific user agent? Or what was the username specifically accessing? We can use this policy language, for instance, to create a document which would allow access to only a private part of the data lake. This is an example of an IAM policy document, and it would say that I can get access to the My Data Lake bucket on S3, but only be able to access prefixes which included my own username. So if I was going to access any data, it would be private just to me. And this is a feature that's supported just natively in the S3 security model, which is provided by IAM. We can also federate identity and access management features through your Active Directory or OpenID providers like Amazon, Facebook, or Google. So the AWS Directory Service provides an AD connector, which will then allow you to administer your identity and access management users, groups, and roles via Active Directory groups. And this gives you the ability to capitalize on your existing investment in business unit aligned security within the AWS storage system. You may also have a requirement for extended or user-defined security. One example of what you might want to take advantage of is the use of the temporary security token service. STS is a feature of IAM that allows you to generate a temporary access token that expires after a period of time. And we refer to a token vending machine, or an API that will dispense a token that allows you to perform an action for a period of time. For example, a mobile device makes a request of the token vending machine to access an S3 bucket. That mobile device has no rights to do so inherently, but the token vending machine supplies a temporary credential that then allows them to go and perform an action, potentially just one action, like being able to put an object into S3, not to read data or to list the contents of S3. When we consider security, of course, we must also consider encryption. And AWS offers a variety of different encryption options, which will allow you to vary the amount of security based upon where the keys are stored and who has access to those keys. At the simplest level, you can take advantage of AWS server-side encryption. This is where we manage the keys and we encrypt all blocks at rest within the storage systems. If you require the ability to control the keys, including things like key rotation and auditing, then you can take advantage of the AWS Key Management Service, or KMS. It's integrated with services like Redshift and S3 so that you can do encryption automatically using the KMS service, which is very, very simple to use and where you retain responsibility for administering keys. And at the top of the security tree, we would place the Cloud HSM service, which gives you access to dedicated tenancy hardware security modules. These are certified infrastructure that are designed to allow you to administer keys where AWS has absolutely no access whatsoever to your encryption information. Hardware security modules are designed to shut off or to destroy their keys rather than to allow those keys to be taken out of the system, and designed also, of course, to cluster for high availability so that you can ensure that you have the most secure key storage available. And you will choose HSM or KMS or server-side encryption based upon the requirements of your data. But they can all be made accessible through our data lake service. So an entitlements system isn't just about securing access to data. It also needs to consider access to the keys. With KMS, for example, we create customer master keys, which you administer and audit. All new objects are encrypted with data keys, which are derived from your customer master key, and data is stored at rest only with the ciphertext version of that key being retained. You can then decrypt the ciphertext key in future using the master key and decrypt the data when required. So a secure data flow within our data lake might be, for example, that users request a temporary credential from a token vending machine built on a service like Elastic Beanstalk. That consults the metadata index to determine if the user has rights to perform the action that they required. If they're allowed to do that, then they're returned a temporary security token, which allows them to access keys to perform encryption and to push data into S3. They can then also use a data flow which is similar for the decryption process, but crucially also is securing access to the encryption keys. So the last level is how we access our data lake. And an API and UI can be an important part of the picture. But in fact, in many cases, you may find that the combination of identity and access management, Active Directory federation, and then S3 security model is more than enough to give you the security access you require. We may also require this API model, which then exposes our search services, our metadata catalog, and provides us that security via a token vending machine. You may find, in fact, that you want to drive all of your access to the data lake through this user interface, and that user interface is only built on top of the API that you expose. Amazon's API Gateway gives us a very easy way to do that. API Gateway gives us the ability to expose APIs globally that we can then distribute to our end users either via SDKs or through simple REST APIs. It provides us throttling and monitoring of requests that are coming in and can take advantage of AWS Lambda on the back end to implement our logic. It also does caching and gives us DDoS protection through a service called AWS CloudFront, which is a content delivery network. And we can generate SDKs for iOS, for Android, for JavaScript, and we can also use Swagger to generate APIs for our applications. This can also give us the ability to transform data automatically and test our applications very simply and build a metadata UI and search UI that provides our requirements. API Gateway takes advantage of CloudFront, which is our global content distribution network, and provides caching, access to endpoints that sit on EC2 or public services that you wish to expose even through your own data centers. So the UI architecture would be that our users get identity and access management rights to hit an API gateway. The user interface then is built on top of that API, and we use a combination of AWS Lambda to consult the metadata index from our API, and then use a token vending machine, for example, on Elastic Beanstalk, which is a managed application container. So how do we put this architecture all together then? A data lake really is a foundation for highly durable data storage and streaming, ingest, and processing of all of our different types of data. We also require a metadata index and a workflow that helps us categorize and govern the data that's stored within that data lake. The search index gives us the simple ability to discover new data and to determine what data might be specific to a query or maybe based upon regional restrictions. We also require a robust set of security controls, but here we're going to be governing access to our data lake really through technology rather than setting a policy about who should or shouldn't have access and how they should or shouldn't store data. The API gives us the ability to standardize things like how data is organized within our data lake and is a crucial part of how you apply security controls. You can't secure what you don't know is being stored. And then that final mile, the API and user interface can expose these features to internal and external users. And certainly where we have data scientists accessing our data lake, we expect that a combination of these raw search services, metadata services, and identity and access management will provide a robust API. So at a very high level then, we have an architecture where API gateway and our user interface sit at the top of access for end users, and we use a token vending machine, if required, to generate access credentials. Kinesis is used to ingest data into S3, and storage lifecycle policies are used to manage the cost of our data over time. Events from this storage environment are received by AWS Lambda and maintains a metadata index and a search index so that we can discover new data via our API. And then lastly, everything must absolutely go via our entitlement system, which may be based upon metadata that has to do with data classification, and also the ability to apply regional restrictions or masking based upon your requirements. With that, we'll open up the floor for Q&A sessions and also to do the poll, and I'll hand over to our administrator for the webinar for more information.
Okay, thank you, Ian, for a great presentation, and Motaz for engaging with our audience throughout the presentation. At this moment on your screen, you'll see 3 live poll questions on the left-hand side. Please take a moment to respond to those polls by clicking on the radio buttons and give us your feedback. We will start addressing some of them, but apologize in advance that we might not have time to get to everyone's questions. So we have we have about 10 minutes left, so feel free to continue submitting our questions at this time, and I will hand it back over to Ian to respond to a few of the questions verbally. Thank you.
Great, thanks, Ryan. We have a question about HIPAA compliance on S3 and whether S3 can be used to store HIPAA data. HIPAA compliance is an area of particular legislation for healthcare data and places requirements on how your data is protected, of course being very sensitive data. At its heart, S3 would not be giving you protection for HIPAA compliance inherently because you have to apply your HIPAA storage policies on top of that data. So S3 would be providing you the raw storage, and you would need to consider HIPAA compliance certainly on the basis of where in the world you stored data on S3. So for example, AWS operates many public regions today, and HIPAA data, HIPAA being a United States requirement, you would then use a region that was within the United States, and we offer 3 of those today. We have 2 on the West Coast and 1 on the East Coast. S3 is designed for the United States as S3 standard, which means that we can stretch that data across the United States, and certainly you would need to use US standard for HIPAA compliant data. But there are also additional compliance requirements for how you encrypt and mask that data, and also how you move it through an application, and those tend to be far more important than just the data storage on S3. Another question that was asked was whether or not we have any case studies and or use cases of storing this data. Yes, absolutely. S3 is, certainly a foundational technology, and data lake technology is, being used across many different types of customers. One thing that's important to remember, though, is that data lake is not necessarily a very easily defined term. Data lake means a lot of different things to a lot of different people. What we can say is, for instance, Netflix has talked about building their core data warehousing based upon Presto and storage on S3. And we have case studies, for instance, with FINRA building a market analysis system that's based upon S3 and Elastic MapReduce. We have many, many case studies, and we would certainly encourage you, if you just do a internet search for AWS Big Data case studies, we have a page specifically dedicated to all of the case studies that are applicable. And furthermore, at reInvent, we heard from customers like Telepart, which is a division of Twitter, talking about how they use S3 for core storage, and also Redfin, which does real estate data management. And S3 is at the heart of their data lake architectures, and they'll be exploiting a variety of different requirements. But what is certainly consistent across all of those use cases is that customers that do planning up front around how they organize S3, how they consider compression, and how they store data formats is extremely important. And so certainly would encourage you to review those and ask any subsequent questions about specific case studies. So another sort of aspect of that, and I've got three questions outstanding at the moment around, what are the use cases for data lake? The customers that are pursuing a data lake architecture are typically ones where either they need a very simple way of integrating new data into their environments, and they need to be extremely agile, but they also need to maintain governance over that data. They need to be able to control things like who has access to new data, or they simply want to place some partitions between business units for how they store data, but be able to take advantage of that high durability and low cost for data storage. One of the other use cases that we see driving data lake is where customers have many, many siloed data stores, and where they need the ability to bring lots of disparate types of data together. Both of those use cases ultimately have at their heart the ability to ingest any amount of data without having a long process up front to bring that together. And I think crucially are focusing on what we kind of refer to as model on read. So the idea of model on read is that customers want to be able to store their data without having a lengthy process of cleansing it before they're able to ingest it and make it available to end users. And so data lake use cases really are all about bringing all of that data together, being able to let customers model it when they go to pull the data back out, but also have sensible constraints on how data is used, where it's stored, and so on. So a great example is customers need to ingest data from an application. That application perhaps is handling HIPAA data. And so they're able to lock access to the data lake just to those regions where they can implement HIPAA compliance. If you have further questions about what other use cases we see for data lake, please do fire those into the Q&A. But I would say then further, ultimately what use cases people are bringing are actually very traditional analytics requirements. By traditional, I mean they're the same sorts of problems that you're going to be solving today, but with point solutions of individual Hadoop clusters or individual databases within your applications. Lots of customers come to us and say, well, regardless of where this data is coming from or what its legacy is, we can add significant value by bringing that data together and exploring new ways of looking at the data and also adding new types of data. A great example would be if you have a traditional call center system that's running on a structured database, and you want to be able to pick up sentiment analysis of somebody who's raising a support call. You could then look at tweets and see if they've had any tweets that indicate that they were unhappy. And that's a very different type of storage required than a traditional database. a very different type of processing, and so on. But really the use cases are endless. What sits at the heart of it, I think, are these fundamental concerns around data security, data organization, data access, and ultimately enabling their end users to put any type of analysis against the data in the data lake. I think for the questions that have been assigned to me, that is all that I've got in front of me, and certainly happy to take more from Moataz. We have 3 minutes left in today's webinar, and I would just certainly like to thank everybody for your time, and certainly please don't hesitate to get in touch with AWS on what your requirements are for a data lake solution. We've got one last late question coming in, and has to do with how we see customers unifying data between a data lake and data warehousing. And that's a great question, and it comes up very frequently in terms of how should you reason about where data lives. In some cases, if you're ingesting data that is fundamentally RDBMS data, then you may find that it's appropriate for a big part of your data lake strategy to be really oriented around enterprise data warehousing, using services like Amazon Redshift to ingest all of those different data sources in near real time, and even perhaps by using the AWS data migration service, which has the ability to replicate data into Redshift. It isn't necessarily the case that by investing in a data lake strategy, you're going to reduce the value of your data warehouse. Data warehouses are extremely useful in that they give us a very simple access model for very well-structured data. But I think the complement needs to come from what is the data that either is lower value, and so you don't know if you need to provide compute within the data warehouse in order to be able to store that data and provision cores over time within a database context. And then also the types of data that simply don't fit in a database very well at all. This is going to be natural language data. It's going to be maybe the output of models which are more machine learning or predictive in nature. And so I think that what we see customers doing typically is that they will either orient themselves around their data lake being really a hybrid architecture with data warehousing continuing to be extremely important and then enhanced with additional data sitting in a data lake. There is also a model that we see very frequently, which is where customers want to move to a model where the data lake is the data warehouse. In this model, they're going to store data using file formats which are appropriate for highly structured data, like ORC and Parquet, and then use SQL engines on top of that data on S3. So for example, Elastic MapReduce supports Impala, Spark SQL, and Presto, all of which give you very high performance SQL access to that data, and then you can shut it down again. And so it really depends on what are your requirements, how do your end users access data, and what is the most appropriate solution. And in either case, we certainly see customers using a combination of data warehousing and S3 to facilitate the data lake strategy. And I think with that, we're going to be out of time today. We thank you again very, very much for attending today. And I will hand it back to our administrator for closing off the webinar. And again, once again, thank you very much.
Thank you, Ian. I'd like to extend a special thank you to Ian for presenting and also Moataz for answering the audience's questions. If you have any comments on the previous and upcoming webinars or suggestions on the topics you wish AWS may cover in future webinars, please feel free to email aws-webcasts@amazon.com. Your feedback will help us to improve our webinar programming.